Did you know that you can perform bioinformatics analyses on clinical data without any programming skills? We introduce AI Hope, an AI-driven system designed for experts to analyze data through simple natural language commands. AI Hope uses large language models to understand instructions. It converts them into executable code and running the analysis on locally stored data. Important discovery tasks in clinical research, such as identifying biomarkers, studying disease progression, and evaluating treatment efficacy, rely on comparing groups stratified by clinical and molecular characteristics. AI Hope can integrate clinical and genomic data to accelerate these discovery efforts. By using natural language queries, it enables subset comparisons for clinical prevalence and survival analysis. AI Hope's power was demonstrated in 2 case control studies using TCGA data. It found TP53 mutations were more common in late-stage colorectal cancer than in early-stage cases. Additionally, it revealed a strong link between KRAS mutations and poorer progression-free survival, PFS, in FOLFOX-treated patients. Our first demo focuses on examining TP53 mutations in early-stage and late-stage patients from the TCGA cohort. Let's launch AI Hope on your computer. The workflow starts by selecting case and control samples from your dataset using simple natural language queries. All datasets are stored locally in the data/folder. Each dataset includes a data table with samples as rows and attributes as columns, like this. For instructions on how to install the data for AI Hope, check out the wiki page on our GitHub repo. The workflow begins by asking users to specify the dataset name for case samples, followed by control samples. For example, if you want to load the TCGA colon cancer dataset, you would enter the name TCGA_code. After entering the dataset name, users can choose how to proceed. If you're unfamiliar with the dataset, you can explore its attributes and value distributions by simply saying, "Show me the data attributes," or "I want to see the available clinical attributes." AI Hope will provide an overview of the installed dataset to guide you in exploring the data. Next, AI Hope will ask you to enter a data attribute, and it will display the distribution of its values. For example, if you type age, you'll see a histogram and a smooth distribution curve. The histogram shows the frequency of values, while the curve highlights the central clustering and spread of the data. Before comparing TP53 mutations in early-stage versus late-stage patients, it's helpful to check the distribution of tumor stages. AI Hope generates bar plots to show this distribution for the non-numeric column tumor stages. The top plot displays the count of each unique value, while the bottom plot shows the percentage representation of each value. Now, let's select late-stage patient samples for our case group. Simply tell AI Hope something like, "I want to filter the cohort," or set up filtering criteria. AI Hope will guide you through the process of subsetting the data. Selecting samples is easy. You just provide a logical statement, and you can even combine multiple statements for complex conditions. For this example, we input, tumor stage is in T3 and T4. AI Hope immediately displays a pie chart showing the number of samples selected. Once you've finished selecting samples for the case cohort, simply say, "I am ready to proceed," or "Let's move forward." Selecting control samples works the same way as selecting case samples. Here, we load the TCGA colon cancer data again and choose early-stage patient samples. We use the criteria, tumor stage is in T1, T2. After controls being selected, we proceed to the next step. You've successfully defined the case and control groups. Now it's time to choose the type of analysis you want to run. You can select the odds ratio test to evaluate the odds ratio based on clinical conditions by saying, "Perform an odds ratio test." Or, you can choose survival analysis to examine survival outcomes in the 2 cohorts by saying, "Analyze survival of patients in the 2 cohorts." To examine the enrichment of TP53 mutations, let's proceed with the odds ratio test. To test the enrichment of TP53 mutations, we set up the criterion TP53 mutation status is 1. This statement indicates whether the TP53 gene is mutated, 1, or not mutated, 0, in the TCGA patient cohort. Once the criterion was set, AI Hope determined whether samples meeting this condition were more common in the early stage or late stage cohort. AI Hope found that 65.77% of late-stage patients had TP53 mutations, compared to 50% of early-stage patients. With a p-value of 0.024, this shows TP53 mutations are significantly more common in late-stage CRC. These findings align with established literature and demonstrate AI Hope's ability to generate meaningful insights independently, without prior assumptions. Now, we move on to our second demonstration to verify whether KRAS mutations are associated with poorer progression-free survival, PFS, in patients treated with FOLFOX chemotherapy. The FOLFOX regimen includes leucovorin calcium, fluorouracil, and oxaliplatin. We defined the FOLFOX-treated patient using the criteria, agent is in, fluorouracil, leucovorin, oxaliplatin. Here, agent refers to the data attribute specifying the FOLFOX agents in the TCGA data. We want to compare FOLFOX-treated patients with and without KRAS mutations. The case cohort is defined using the criteria, agent is in, fluorouracil, leucovorin, oxaliplatin, and KRAS mutation status is 1. This example combines multiple logical statements to create a complex condition. When using multiple statements, each must be enclosed in parentheses to maintain clarity. The control cohort is defined as agent is in, fluorouracil, leucovorin, oxaliplatin, and KRAS mutation status is 0. AI Hope uses user-defined case control groups to generate Kaplan-Meier plots, showing survival probabilities for each group. The log-rank test evaluates differences between survival curves, and Cox regression calculates hazard ratios, HRs, to assess the impact of groups and variables on survival. Users can choose between univariate analysis, focusing on case control groups, or multivariate analysis, which adds extra variables to explore combined effects on survival outcomes. The analysis identified a significant association between KRAS mutations and poorer progression-free survival in FOLFOX-treated CRC patients. These findings highlight its capability to produce actionable insights aligned with established scientific research. Overall, AI Hope simplifies precision medicine by integrating clinical and genomic data in a user-friendly, LLM-powered platform. It enables advanced analyses without programming skills, showing success in studies like TP53 mutations in CRC and KRAS-related outcomes. Running locally, it secures data and supports biomarker discovery, disease research, and therapy evaluation. Future upgrades will add new tools and multiomics capabilities, accelerating discoveries and improving patient outcomes.